Welcome to TransMed's breast cancer survival analysis demonstration. By integrating clinical and molecular data, it becomes possible to identify correlations between molecular characteristics, such as variants, and clinical characteristics, as in this survival case analysis. This same sort of analysis could be used to find variants or gene expression patterns that correlated with differential response to treatment as part of a personalized medicine research program. To start this exploration, we will log into TransMed BIS with TCGA breast cancer data. To do so, open a web browser and go to the URL provided with your BIS free login info. Once loaded, you should see a screen like this. Log into BIS with the username and password provided, and select the checkbox to agree to the terms of use for BIS. Once logged in, you will see the Project Explorer home screen. Logging into the system controls what data you have access to, including whether you have identified or de-identified access to a particular project. Having user identities in the system also allows control of user artifacts, such as cohorts, reports, and analysis results. These can be created, saved, and shared between users of TransMed on the basis of user identity and role. What you are looking at is the Favorites view. Since you do not have any favorites, it is empty of workspaces. A workspace is where you will be doing all of your work. To get to the workspace that was created for you to work in, we will need to view all workspaces available to you. This is done by selecting the drop-down called Favorite Workspaces and selecting the option called All Workspaces. Once you select all workspaces, you should see a workspace, specifically a workspace with your login name as part of its name. Once you locate it, double-click on it to open the workspace. This will open the Workspace Explorer tab. At this point, you will see the contents of the workspace. In the workspace are some pre-populated artifacts that are the results of running this scenario. We will not be using these here. We will create them from scratch, but have made them available so you can look at them as a reference. Workspaces are the folders that contain all user artifacts that are created by a user. Artifacts are organized into workspaces such that users working on the same analysis project can share items within the workspace and collaborate together on the project. This scenario utilizes Cohort Explorer, so we will need to open the Explorer. In the Tools drop-down, select Cohort Explorer. This opens the Cohort Explorer tab and shows you the unfiltered cohort of all available patients in the right portion of the window, and the available data, or traits, in the left. The traits are organized into folders, just like Windows files in the directory structure. You can at this point double-click on those folders and explore around. There is a back button and an up button below the Tools drop-down. Use these to return to your previous position. As you drill down into folders, there is a graphic representation below the back button, showing you your location in the hierarchy, with the highest level being All Items. These are hot buttons as well, so you can return to the highest level by clicking on the All Items button. To begin this scenario, be sure you are at the All Items level. PI3K variants are the most common oncogenic variants in breast cancer. In particular, PIK3CA has activating variants in a large percentage of breast cancer variants. Cohort Explorer provides an easy way to find out what the breakdown of mutations is within the cohort in your research center. To begin with, we're going to look for those patients with the molecular variant gene symbol PIK3CA. To do this, we could navigate to the molecular variant folder and view the gene symbols. This works if we know where to go. However, let's assume that we do not know where to look. So the alternative way to find it is to use the search function. In the search box, type PIK3CA and type return or press the magnifying glass icon. When the search is complete, you can see the discovery of the gene symbol PIK3CA in the search results. Selecting the result causes a filter icon to appear. This opens the Filter Options dialog. Click on the filter icon. Once the filter options are open, Notice PIK3CA is part of the gene symbol trait in the molecular variant folder. PIK3CA is automatically selected as part of the navigation to the filter from the search results. You can see there are 15,819 possible choices in the list, of which PIK3CA is one. If we wanted to look for another symbol, we could use the Search Choices box above the list. Selecting the Apply Filter button or executing this filter will take the existing cohort of patients and reduce it to those with just the PIK3CA molecular variant. The new cohort has 263 patients, down from 772. Now we want to investigate the relationship of different amino acid changes. To do this, we need to navigate into the molecular variant folder. This is done by returning to the All Items level by clicking the All Items button above the search box. This returns our view to the top level. Navigate into molecular variant by double-clicking on the folder in the navigation window. All the traits contained in the molecular variant folder are now displayed in the navigation window. Amino acid change is listed right at the top. The list is alphabetical. If we wanted, we could use the search to find it as we did for PIK3CA. Within Cohort Explorer, it is also possible to get the breakdown of the variants within a particular gene. This is powerful because it allows us to easily identify the relative frequency of individual variants. Here the data is broken down by the amino acid change, but we could easily break it down by activating or damaging variants, for instance, if that annotation was available in the system. Further, we could also apply a filter here and identify the patients with a particular PIK3CA variant, or only those damaging variants. What we want to see now is how many of these PIK3CA variant patients fall into each of the amino acid changes. To do this, we're going to group the current cohort based on specific amino acid change types. Find and select amino acid change. Notice that when you select it, a few icons show up. One looks like a funnel, and one that looks like a group of people. The funnel allows you to filter the cohort and reduce the cohort to only those that match the selection of amino acid changes. The grouping option takes the existing cohort and splits the cohort into groups based on your selection. We want to group on specific values. Select the Group On icon. Once you are looking at the grouping options, select Group by Individual Choices to group the current cohort into different groups, one for each value of amino acid change. Now select the Group button. The cohort on the right is now organized into different groups. The summary tells us that there are 65 groups. Each icon shows the value, the count for that value, and the percent of the total count that value represents. Our goal here is to look for amino acid changes that are significant. So first thing we will do is use the sort feature located right above the icons in the banner and sort the values so the highest counts are at the top. Select the 9 to 1 option. The result is that the amino acid changes with the highest count are bubbled to the top of the display. We also might find value in changing the view from an icon-based view to one which shows the group details. This creates a table of amino acid changes with the count and percent values. The group details view is nice for publication of papers. It gives population frequencies and proportions, which are often required for publication. After looking at the different views, return to the icon view. If we wanted to narrow our cohort to just those patients with one of the specific amino acid changes, like H1047R, the one with the largest count, we can double-click on the H1047R icon. The result is a cohort with the reduced count of 102 patients. Also notice there is an additional breadcrumb on the right side of the display called amino acid change, molecular variant H1047R. This breadcrumb is the one created based on applying the filter to narrow the cohort to those with H1047R variants. For our purposes going forward, we want to return to the previous cohort. To achieve this, we simply click on the gene symbol molecular variant PIK3CA. This is the breadcrumb just to the left of the amino acid change breadcrumb. This will return the cohort to the previous count of 263. Now what we want to do is determine if any of the amino acid changes have a statistically significant impact on survival rate. To do this, we will create a report including the data needed to complete the survival analysis. The first step is to create a base report. To do this, we click the Create Report button above the breadcrumbs. This launches Cohort Reporter and pre-populates it with a basic template. The purpose of this study is to determine if there is any biological difference in regards to survival rates of patients with different variants of PIK3CA. Although this is just an example study, it does show the power of the tool and the sorts of analysis that can be easily envisioned within the tool. In particular, this demonstration focuses on the integration of outcomes data and molecular data. If the pool of patients, outcomes data and treatment data was larger, it would be possible to perform more interesting clinical analyses, like whether the variant identified in the study was associated with differential response rates to PI3K, AKT, and mTOR inhibitors. To complete the survival analysis, we need to add some additional data values to the report. Adding the traits that we need is straightforward. It can be done a couple of ways. If we know where the trait exists, like amino acid change and gene symbol are in the molecular variant folder. To do this, we right-click on the molecular variant box and select Edit Level. When we do this, we can see that the gene symbol is already selected because it was used as part of the cohort definition. So all we need to do is select amino acid change. Amino acid change is at the top because it is alphabetical, but if it were not, we could use the search at the top of the list to find it. Select amino acid change and click OK. Notice amino acid change has now been added to the report template. The next trait we need to add is vital status. To do this, let's use the search in the navigation window on the left side by typing vital in the search box. After you press return or the magnifying glass icon, you can see vital status in the results window. When you select vital status, a plus sign appears. Clicking on the plus sign opens the trait option window for that trait. Also notice that the results tell you which folder the trait is in. In this case, it is patient. In this case, we want all the choices in the list, so we only need to add the trait to the report by clicking OK. This adds vital status to the report in the patient folder. The last trait we need to add is survival time. Following the previous steps, search for survival time, select it, notice it is part of the diagnosis folder, and add it to the report by pressing the plus sign to bring up the options dialog. Click on the OK button to add it to the report. Now we are ready to generate the report. This is done by clicking on the Save and Close button, located in the upper left, right below the BIS 5.1 icon. This will bring up the Save New Report dialog box. Give the report a name, something like Breast Cancer PIK3CA Report. Once you have entered the new name, click the OK button. This will bring up a dialog asking if you want to generate the data now. Select OK. Following the generation of the data, the report will load. In the report, you can see the data. Along the top of the report, you see the title of the column, and each row represents an entry. If you scroll to the left, you can see all the traits. After reviewing the trait values, let's create a survival analysis to look a little deeper into the amino acid changes and how they relate to the PIK3CA gene. To create the analysis, we need to open the Analysis Tools by clicking in the Navigator window on the Analysis Tools icon. This will display the various analyses that are possible in our base product. Select the Survival Analysis tool icon. To run the analysis, we need to fill in the grouping column, outcome column, value representing death, and survival time column. Each of these is a drop-down choice list. We will use these values. For grouping column, select amino acid change. For outcome column, select vital status. For value representing death, change the text and input deceased. For survival time column, select survival time. Once the analysis parameters are set, execute the analysis. There is one line there that looks like the survival time is significantly longer than the others. So let's look at the Data Results tab located at the top of the graph. The data results can be sorted just like an Excel spreadsheet by clicking on the column header. Sort the results on the p-value and scroll down looking for the one with the lowest value. About 3/4 of the way down, we find the first non-zero value, and it is for H1047R versus N345K. The p-value for this pair is 3.576 times 10 to the minus 7, or statistically significant. The noteworthy finding here is that there is a significant survival disadvantage for the N345K PI3K mutation. Even after correcting for false discoveries, such as data not shown, the result is significant. This might mean that these patients are particularly strong candidates for PI3K, AKT, and mTOR inhibitors, or at least this is a hypothesis that might be worth testing in the laboratory. This concludes our breast cancer survival analysis demonstration. Thank you.